Okay, well, thanks. First, I want to thank the organizers for putting together this great symposium. So I'll just give you a bit about what we're doing. So I'm a computational chemist, material scientist, and we've been for some time now looking at solid sorbents for CO2 capture. And this technology has actually been used to scrub CO2 from natural gases for like over 50 years, using pressure swing absorption systems where they use zeolites as the sorbent, and they're packed in these beds. But combustion fluids have water in them, and the zeolites get poisoned by water, so new sorbents are needed. And one of the sorbents that has attracted the most attention are these so-called meta-organic frameworks. So these are nanoporous materials composed of organic linkers and inorganic nodes with metals in them that can self-assemble to hopefully form a permanently porous network. And what's attractive is you can use sort of a range of different linkers and nodes. And so this here shows just the diversity of the porous structures that have synthetically been made in the lab. And of course, the promise is that they're highly tunable for any application you want. So before I get into the talk, just what we've been doing for a number of years is basically data-driven methods for MOFs. So we were the first to do it. So we have a number of high-throughput screening and machine learning models, and it's just some of the data-driven methods. So what we did here, we screened a database of about 320,000 MOFs, looked at the high-performing materials with some simple metrics, extracted out the binding sites, the CO2 binding sites, and then did a similarity analysis of about 100,000 of the best binding sites, and then targeted the binding site rather than the whole MOF for synthesis. And so our partners were able to make this, what I call this aromatic sandwich, where we have aromatic rings about 7 angstroms apart. That it's good for CO2 capture under wet conditions, and it showed exceptional performance under very high humidity. So usually those humidities, the water just condenses, and then and that the computational work at least was the PhD thesis of one of my former students. So in terms of commercialized MOF for CO2 capture, we've also been involved with a MOF that was developed in George Shimizu's lab and commercialized by actually a Canadian company called CEMDI. So it's a MOF called CAF20 that has been used at the pilot scale on a real without years. With so I'm getting barge to them, and they can make it in 1.5 ton batches. So they're pretty serious about that scale. And so they're because the CAF20 and actually been doing on local basis. And so they're in the MOF field to do high throughput screening and build and are generated MOFs, and there's, new ones coming out that are fairly large. But the most commonly screen databases and ones used for building machine learning models are actually of experimentally characterized MOFs. So they call them computational ready experimental MOF databases. By far the most common is this core database, which just in 2023 alone was cited 200 times, most of them papers doing screening and building ML models on these. So why do we have to call it? I mean, if they're experimental structures, why do they have to be computational ready? Well, all of these structures come from the CST, and these are single crystal X-ray diffraction structures. And so when you get the results from those experiments, you can have disorder. That's, where you have a few low energy conformations that are diffracting. So you have to sort of clean those up. The method doesn't pick up on the protons, so you have to add protons. And when the MOFs crystallize, it usually crystallizes with some co-crystallants or solvent, and so you have to remove that to make the material porous. And they do that experimentally by activating that. And then lastly, the framework itself can have a charge. And so if you remove the counter ion, you have to label the framework as charged. Otherwise, your computation will not be particularly accurate. And so like with many people, we also screen the core database, and we screened it for direct air capture. And we did like the calculations to get charges on this, and we had this hit called CEMDI, and this is just a reference code that the CSD gives a structure, but that was from the core database, which is supposed to be clean. And it was very high performing. I was a bit surprised, but nonetheless, that's great. But then we looked at the structure and we saw that the yttrium was in a +7 oxidation state, which is actually impossible, because it doesn't have that many valence electrons to give away. So just some background, if you're not a chemist, metal oxidation states are just the electron counting formalism that we use. We teach in undergraduate chemistry. It's basically just the charge a metal would have if all the bonds to it were ionic. Poorly, it's not a physical property, but most metals are only known to exist in 1 or 2 oxidation states in stable compounds. There are obviously some metals that have lots of oxidation states, but for example, cadmium is almost exclusively in a +2 oxidation state. So that's what oxidation states are. So back to this, obviously there's clearly a problem with this structure that's supposed to be clean. And we went to the original paper and we found that the oxygens, actually, those were not part of oxoligands, but they were part of aqua ligands. And if you do your electron counting there with the aqua ligands, then yttrium is in its familiar +3 oxidation state. So they had not put the protons back properly when they created that database. And it's normal not to have the protons in the CSD structure because the experiment doesn't pick up on it. Oh, and importantly, yeah, we then redid the calculations. It was pretty low performing. So we looked at other structures, this Dunzu structure labeled as a neutral framework. If you calculate the metal oxidation state, it's +3. That's basically unknown in MOFs. Sorry. And so again, we went to the original paper, and turns out they had removed the counter ion, but not accounted for the charge. So the framework actually has a -4 charge, and then if you do your electron counting, it's happy it's in its +2 oxidation state. So we started thinking metal oxidation state be used to detect problem structures, because In this case with Dunzu, there's nothing wrong with the bonds. Bond distances are all normal. Everything's fine. It just was mislabeled. So maybe it could be used to detect these problems that as far as we know, there are no existing automated tools to address. And so we spent more than a year developing this code, but we have a code called Mosaic that it's, as far as we know, the first algorithm to calculate the metal oxidation states of metals for the structure as given. So that's important. If you give it an erroneous error, it will naively calculate the oxidation state of that structure. So it should be sensitive to errors, and it's fairly general, which I'll show you. So we paired it with an error flagging routine so that if it computes the oxidation state and sees it's impossible or rare or whatever, that there's probably a problem with the structure. Non-integer is also a problem. So this was conceptually simple. I thought this would be a short project, and because we teach our third-year undergrads, second-year undergrads sometimes too. But it turned out to be a monster to implement in a general way. And the challenges are, what you have to do is calculate all the formal oxidation states of all the non-metals in your system. And you don't get a nice Kendra structure with the double bonds, that's aromatic, all that stuff. You're just given, boom, a bunch of coordinates. And then in MOFs, at least, there's really diverse metal bonding environments. You can have ligands that bridge different metals, and then you have all these charge sharing networks that make it challenging. But I'll show you, I think we have a robust method, but this is just to show you the what has to be done. So first you break all the metal bonds. Then you have to calculate all the oxidation states of all the nonmetals. That's a challenging part. You have to then group those charges into binding domains, and then partition the charges to each metal in the binding domain. And then you get initial oxidation state assignment, which is terrible. They're non-integer. But it turns out when you add the metal, this whole structure can share its charge. So when you do that, you identify the charge sharing networks. They can share their charge, so then you end up with a good +2 oxidation state for zinc, which is what you expect, and this is a good structure. You can do the same thing for a bad structure. This aluminum one, again, I won't go through it in detail, but the whole thing shares charge. And so you end up with non-integer charges, which is an indicator that it's a bad structure. And indeed, if you go to the original publication, they didn't account for the counter ion. So how accurate is it? So this is where a lot of the work went into in this work. So we took about 2,800 good MOFs and about 2,700 bad MOFs. So we went through each one and said, okay, this is good, this is bad, by comparing to the original papers. Those original papers have, at least in the ones we picked, the oxidation state assigned. So we're taking that as the ground truth. And for the good MOFs, where we don't have a structural error, it's pretty accurate at predicting assigning the right oxidation state. For the bad structures, that error should make the oxidation state wrong that we calculate. And in fact, it's wrong 94% of the time. So that's exactly what we wanted to be able to detect errors. Now, how does it do in detecting errors? Well, we by hand manually went through 16,000 of the core moths and examined them to the original papers and labeled them. Well, when Mosaic says it's bad, it's 95% accurate. So at least for detecting bad structures, we think it's very good for that. It's has a 15% false good rate, but that's because the error might put the metal into a different oxidation state, which is also common and so okay. So then it says it's okay because the oxidation state isn't impossible or whatever. But certainly if it says it's bad, it's very likely a bad structure. And Mosaic's pretty fast. We can screen millions of structures, and we have. And what we've done is we've gone through a whole bunch of moth databases and looked at the error rates. So these are the error rates, the name of the database. This, for example, is the core database, which everyone uses. It was highly cited, and those are the size of the databases. So yes, the number of the error rate in the field is shocking. Okay, so these moths have this, the database that everyone uses has a 50% error rate. And even these, we picked these ones because they were published, they're new ones. This one is particularly bad because they took these structures and performed 30 million DFT calculations on them. So this problem in the field is not a good thing. And there are, so what does it mean for screening studies? This is obvious, probably for most people. You get false hits. But the bad structures really are not chemically sensible. It's like if you were screening for molecules for drugs, and you put in molecules with carbon atoms that had 7 bonds in them. Sure, it might make a good drug, but it's not stable and it's not going to be synthesizable. So these bad structures are not are at the same level of error. And also, when you have like 50% of your structures bad, you're not screening the real space that corresponds to those structures that you replace with erroneous structures. So that's also a problem, not only with wasting the computing time. ML models, well, that's very hard to generalize. There's so many different varieties of those. Really depends on the properties, but we're sort of looking into that for right now to see building models for common properties with completely with these wrong structures and seeing what happens. Okay, so where do the errors come from? Some of them come from the limits of the XRD experiments, but those are well known. Protons sometimes aren't well resolved, there's disorder, but it turns out the majority of the errors from our analysis come from the solvent removal algorithms. So these pre-processing algorithms people were using. For example, the core structures, 50% of the errors, so a lot of them come from missing protons, but 50% also come from the wrong charge assignment. So they remove the counter ions and didn't account for it. And then, of course, when people were building hypothetical moths, they used building blocks from this database. So that's where all those, why some of them have 70% errors. So what can be done? Well, if you notice, there are 2 databases, large ones that don't have any, well, low errors. That's 5% sort of the error window of the method. ArcMoth is our database, so we use the Mosaic to get rid of the structures. But QMoth, partly what they did was they did full DFT geometry optimization, and if the structure didn't blow up, then they kept it. They also use very strict processing criteria. So if they had anything to do with ion or charge framework in the paper, they would discard it. They wouldn't even try to fix it. Any moths with any disorder, even simple disorder, they removed, and they removed the only solvent that was in the middle of the pore, not anything attached to a metal. And so what we've done, the other thing we can do is use the oxidation state to inform the pre-processing, and that's what we've done with a method we call SIMOSA. So basically, we only remove solvent that doesn't change the oxidation state. And again, we have to validate this. So we took 2,000 moths, manually performed solvent removal on them, and we chose 50% on purpose with structural errors, because a lot of the structures in the CSD have structural errors. It's just the way the experiments are. And so if you have a structure that Mosaic says is good, it's very accurate at doing the solvent removal properly. Even if the structure has an error, it's not so bad, because some of the errors can be pretty severe, but it's still doing the right thing. Of course, if you want a really high fidelity database, then you you get Mosaic to flag if it's good, and then you apply this method, and then it's pretty safe. Okay, so what about correcting the errors? Well, Mosaic only flags if they're bad structures. It doesn't fix them. We decided to develop machine learning models. At least the first step is to classify the errors so you can fix them later. And we had all this data we had manually labeled. So we developed a graph attenuated neural network to do this. It flags the error properly with pretty good accuracy, in my opinion, considering you're just giving it coordinates, and that's all you're doing. Okay, so time is I have 22 minutes here, and we started late. So are we going to?
Yeah, you have 5 more.
Okay. All right. So conclusions. We've developed a hard to detect structural error methodology called Mosaic. Shockingly, alarmingly, most databases in my field are full of these errors, so this is not a good thing for the field. And I think we've made some movement in terms of fixing these problems. So we've curated a good database of materials. Going forward, I mean, people are working on generative models of moths. So if you're going to do that, you have to produce them with good metal oxidation states. And we've only applied this to what I use in my field, but of course, it might be interesting to look at other databases, which we haven't, but you know, I don't know. And not all the kinds of materials are applicable to this kind of problem. So then I'll just very quickly talk 2 minutes on some of our work on invertible encodings for moths. So we have a coarse grain invertible encoding, so that allows you to utilize variational autoencoders. So you're digitizing the structure of a moth with just the SVUs and the topology. But that's like big coarse grain. But are there atomic level encodings? Well, for molecules, we all know about that. There's smile springs. You can get structures. The challenge with periodic crystals is they have to be invariant to the lattice vectors, because there's not a single lattice vector that defines the periodicity. There's a bunch of them. So as far as we know, and others may be, because we're new to this field, but others in the might have, know, more state of the art, but as far as we could tell, the slices encoding for periodic structures is the state of the art. They said it was 95% invertible for small inorganic crystals. But it requires a force field optimization, and it's actually not invertible with the lattice vector. So that can be a problem because you can have a structure, if that's how they're defining it, then you can have one structure give different encodings, which is not what you want. You need it to be invariant. They tested it on this QMOF database that I mentioned, and it was only able to decode 3% of the database. So we developed an atomistic encoder for periodic systems. I can't say too much about it, but at least for QMOF, it's more than 90% gives the exact structure back after you encode it. And I think, I'm going to guess that 5%, we didn't realize until not long ago that a lot of these MOFs are interpenetrated. So there's a framework within a framework, and it's not supposed to, our method only works on non-interpenetrated 3D structures. So, and so that's all I have to talk about. I have to thank my group and funding agencies, my main collaborators, and then of course you for your attention.
Questions?
Thank you for the interesting talk. I wonder if the tools that the group developed, the project is open for everyone to use, or is thus used in the own group? And the second question is that do you think that the framework you propose here can be adapt to another kind of material system?
Okay, so I think the first question was how open is the method? We haven't published it yet, but we plan to make it open. The database is already published and open. The invertible relationship is really new, so we're not even close. We haven't even started working on a paper for that one. But the code at least should be released for the Mosaic and the Samosa. We should at least release that. Application to other databases, certainly molecular organometallic structures. That's where we can also look for errors. The invertible relationship, I don't know how useful it is, but if it does work, it will work for any periodic crystal. Yeah, did that answer your questions?
Yes, my second question, could you make it in a little bit clearer? If this kind of approach can be adapted to another system.
You mean looking for the metal oxidation states? Yeah, it depends. I mean, the problem that so what we have is we have covalent bonds in MOFs. Should work as well. For crystal, well, I mean, those are more tools for The problem is when you have covalent
The, shouldn't be bothered because we might go in explosive other systems or including the increase in solid effect.
Yeah, okay, so those are really good questions. We do full process simulations. So then we're evaluating, for example, how much energy does it take to remove the CO2? So that's what we're doing now. We do computations to get the absorption properties, heats of absorption, heat capacities. That's all fed into a process level, so macroscopic model, and then it comes out with process specific metrics like productivity and energy. So that's what we're doing now. What we did for that other study is we just use very simple metrics, which don't always correlate very well. In terms of water, what we do with water is those simulations, we can include water, but the error bars are much larger. And so that's a problem, and they take a lot longer to converge. So we usually do a high-level screening, like if it doesn't work without water, it's not going to work with water. Start sort of thing. So then we down, and then we run simulations with water on all our subsets. So that's how we do. Yeah.
Okay, I have one question for you.
Sure.
Why do you think oxidation states have to be neither if the charges are distributed and you have complex structure?
Well, it's just it's what people have found, right? So it's an empirical model that's been used for.
But quantum mechanics may say sometimes charges are.
Well, it's not a quantum mechanical model. It's just the simple model. So it's not like I'm not trying to compute charges.
Yeah.
It's not a physical property. But it's something that chemists have used. And so from the experience of synthesizing a million structures, I guess, and assigning oxidation states, that's what they find that they, yeah. But yeah, it's a heuristic that has nothing to do with quantum mechanics.
Good. Yeah.
Thank you so much for the presentation. I wonder how you link your finding with the experimental.
Yeah, that's a good question. Concerning what though? Concerning the CO2 capture? Okay. So I also didn't talk about the fact that with this collaboration, we also have synthesis partners. So we down select structures and then our partners synthesize them and then test them. So that's how we're doing the link. But we actually spend a lot of time looking at the papers where they synthesize the material and looking for things like water stability, defects, all those sorts of things. So when we down select, there's a lot of legwork involved in doing that. But we do have synthetic partners that make them and then they test them. Another partner actually tests them in the lab.
Sorry, just a really quick follow-up. In that review, do you look into what sort of defects arise within those structures and then use that to fortify your model in terms of the allowed structure?
Yeah, that's a really good question. No, because there's not really a good way of experimentally quantifying defects for the most part in MOFs. And so we can't really do that. Like I said, we sort of look at the papers, and there's some clues to looking for the defects. But like, you know, this famous MOF UIO 66, everyone makes it, everyone gets a different structure. So if we see that sort of stuff where multiple groups are making a material and they get different properties, different, you know, surface areas experimentally, that's probably a, you know, an issue. So, yes, that's a fundamental problem because, is our disagreement with what they get experimentally, is that a problem with our simulations? Or is it a problem with the fact that we're not actually simulating the same structure? Like, is the structure that you make, is it full of defects? Okay, and if we could quantify those defects experimentally, that would be great, but for the most part, that doesn't exist for most of these kinds of materials, at least. So yeah, that's a challenge that we have to sort of overcome.
Okay, let's thank these people.